So I'm Yi from Tsinghua University. I'm doing research on reinforcement learning. So I believe you guys have heard a lot of things about computer vision, right? Visual understanding, embodied AI. So today, let's talk about something about reinforcement learning. Okay, that's a some different flavor. So reinforcement learning is kind of one of the important engine to push the frontier of AGI or AGI products, particularly if you really familiar with the past, what happened in the past 3 years. Basically, reinforcement learning is the key ingredient or the technique that push the AGI power to everyone, to the products. So for example, in 2022, reinforcement learning is the key thing to make large language model to something useful. For example, the IHF, reinforcement from human feedback technique, is the key thing to unlock the LLM power to a product like ChatGPT. And last year in 2024, we have reasoning LL, which is another technique to enable model to think. So the model can solve a lot of very challenging problems like coding, mathematical reasoning or something. And this year we have some new products like agents, right? We have some AI model, not only a text model, but also solving very complex software manipulation problems, a lot of workflow problems. So it can be something like agent. So today in this talk, we'll talk about something about reinforcement learning for agents, or we call it agentic IL. Right? So we want to use reinforcement learning to train an agent model that can do a lot of very complex problems. So what is reinforcement for agents, right? So everyone, if you know something about reinforcement learning, so in the very beginning, reinforcement learning is a technique to play video games. You train an AI to interact with a game environment. So the AI can play video game very well. So you have an agent, you have an environment, which is a video game, and agent can interact with the environment to get some reward. And then you use reinforcement learning to train it. With this kind of thing, we have lots of great projects like AlphaGo or Dota project, something like this. And now we have in the LM era, right? We have something similar to that paradigm of video game IL. Again, we have an environment. It can be a software, it can be your laptop, or it can be your phone, it can be a browser. It's again an environment, and we have an agent. The agent is kind of slightly more complicated because now it's LLM agent, right? You can have you need to implement something to wrap the LLM within an agent framework so that the LLM can interact with the environment. For example, it can control your mobile phone, it can control the browser to interact with the web page or something like that. So you have bunch of this kind of tools or APIs so that you can have a ARM agent workflow, and then you can run reinforcement learning on top of that to scale it up to train the agentic power of the model. Okay, so that's basically how agentic IL or IL works for the agent era. Okay, and then some people may have the question in mind, right? So why do we need reinforcement learning, right? It's because we have all this kind of LM. LM is very powerful. We have the workflow. We have all these APIs. But why do we need to train it? Why do we need reinforcement learning? Okay, so here I will give you agent is a very broad topic. So in this talk, I will give you a very simple example, like the search agent. It's a very simple, basically the simplest form of the agent or the possible agents. So basically just you ask the question and the agent will search the answer online and give you the answer. Okay, so I'll show you that even in the simplest form of agent, it's much more complicated or challenging than you imagine. And a reinforcement learning can really give you a very powerful solution to that. Okay, let's think about a very simple. So before we talk about examples, just give you this conclusion. Okay, why do you need reinforcement learning? Two things. One is simplicity. Agent is very complicated, and if you use reinforcement learning, you can have a much simplified agent workflow. Second answer is the generalization capability. If you really use reinforcement to train an agent framework or train an agent model, you can really observe emergent reasoning capabilities. The agent model can really learn to, basically, or unlock the potential of do very complex reasoning steps. So that's the short answers. So okay, let's consider a very simple, concrete example of why you need reinforcement for agents. Okay, this one. So the question is, there's a search question, a search agent, right? So you have a question. The question is, how many medals of China team won at London Olympic 2012, right? Think about this. This looks like a super simple question, right? So everyone will say, okay, I can use whatever search engine to search for the answer, right? You can, it's super easy. You can directly get the answer. It's 38 gold medals, and right. Well, it looks right. But if you are very familiar with Olympic Games or sports, the true answer is 39. Why? Because in this one particular, I think there's racing walking competition. At that time, the Chinese team got only a bronze medal. But at that time, the gold medal and the silver medal was disqualified for doping. Right. So basically, that gold medal was awarded to China team after 11 years of the Olympic Games. So, right, if you're really familiar with sports or Olympic Games, you will know this. So think about this, right? So the correct answer for this question is 39 gold medals. But think about this. If you don't know the very detail, if you're not a professional sports lover, right? How can you know this? Think about the process. You will search online. You see lots of news, formal news, saying that 38 gold medals, and accidentally you see some news saying that 39 gold medals. It's conflict information, right? And then you will say, why is 39, right? Check it in and see something like disqualified or doping or something like so. What doping means, right? You need to do some new research, and you eventually notice that, oh, if you are doping, right, then your medal will be disqualified. And then, okay, you check the rules of Olympic Games. Oh, that's really the rule. So you need to do a series of questions, a series of search, and eventually can give you the final, very confident answer that, okay, the correct answer is 39. But the China team did get 38 gold medals at 2012. But that's the correct answer. So think about this process, right? It's very, very non-trivial, even if the question is very simple and the answer is verifiable. So we check this with a lot of commercial products. So this is the result with DeepSeek. There's a web search functionality. So we launched this question to DeepSeek. So DeepSeek give you the answer. It's 38 gold medals. Okay, so DeepSeek. So it also tests this on ChatGLM. Okay, GLM by Zhipu. So also have a web search product, right? And we search that, and again, at 38 gold medals. Also test this on ChatGPT web search. And ChatGPT is great because if you see this result, it's basically saying that there are some minor sources showing that there are some different numbers is 39. So basically, ChatGPT really obtain the correct source. But then the conclusion is still wrong because the ChatGPT says, okay, there's only minor sources. Majority of the sources saying 38 gold medals. Okay, so I conclude the answer is 38 gold medals. So ChatGPT is great, but final conclusion is wrong, right? But just a side information, we check the agent mode. The agent mode can get this right. Okay, so you get a sense, right? You get a sense. Even if the question is super simple, even if the task is super simple, it's much more complicated than imagination, right? Okay, so, okay, then let me go through this, right? If you are asked to build up a search agent using a workflow, LLM workflow, like LangChain, DeFi, whatever you like, think about how can you do this, right? Probably you'll think about, okay, I need a search module, I need a verification module, I need a cross-check module, I need a lot of modules, right? So you probably need a very complex multi-agent systems, right? You need a lot of different agents for different modules, so the system will be very complicated. If you are asked to build a workflow agent. Okay, so what about an RL agent, right? If you just train it, if you are allowed to train it using reinforcement learning. So our answer, okay, so that's our project. It's called A-Searcher. It's an open source large-scale project for search agents. So the message we really want to express is, if you are able to run reinforcement learning properly, then your search agent can be super simple. So we'll build up a search agent workflow like this. Only two tools. It's very simple. Just one model, one model, a 32 billion parameter model with reasoning capabilities, and only two tools, only two tools. The one tool is search, one tool is click the website, right? You need at least two tools because it's search agent. You need to search, you need to click the website. So this is a minimalist design of the agent architectures. I want to show that if you do reinforcement right, everything will be resolved end-to-end in end-to-end fashion. Okay. So here's an example. So eventually we run a searcher with a open source model, which QWQ 32 billion parameters with end-to-end reinforcement learning. And then it can correctly answer this gold medal test. And this is a test set. It's not from training set. Okay, just want to double check. Very interestingly, so I would do some brief discussion, brief introduction of the search process. So basically, a searcher got the correct source of 39 gold medals in, I think, on the fifth action or something like this. But eventually, the A searcher learns to double check all these resources, double check this doping stuff, like for 30, or I think for 60 or 70 steps. So after 70 steps, so you got the answer on fifth step, but eventually it continue doing search and double check and reasoning, and after 70 steps, it give you the final answer of 39. So this is something emergent. It's not, we didn't incentivize, we didn't force the model to double check, but this double check or cross-checking capabilities are completely emergent. So here are some benchmark results. So the red bar are something before reinforcement training, and the blue bar is after reinforcement training, and the final bar is basically we introduce some additional models for the tools. So you can see after reinforcement training is basically a 20% or 30% absolute improvement of the test set, the benchmark result. And you can also observe very strong zero-shot transferabilities because you can plug in some new tools and get a state-of-the-art result. Okay, so that's what I want to say. So this project is basically saying two things. If you can run reinforcement training, right? Then your the agent workflow, the agent architecture can be super simplified. So simplified is good, right? You can do a lot of things. So you can do your workflow, your agent model super simplified. Second thing, you can really observe the emergent capabilities, right? Everything is emergent. Okay, so that's the good thing about reinforcement learning, right? But what are the challenges? What's the burden for us to really apply reinforcement, large scale reinforcement to this kind of agent training, right? Basically two things, two challenges. One challenge is data. The second challenge is slow training efficiencies. Okay, so I'll show you basically what are the challenges in details. So first thing, no data. Okay, so here's a comparison between like the existing QA data set and what are the testing set or something you're really tough for the agent. So you can basically have a sense, right? These are the training set and these are something people ask. It's super complicated. So you don't really have any data, right? You can't really have all these questions online, nothing there, right? So this is data problem. You don't have any training data. The second thing is about training, slow training. Why it's slow? Well, we have a conclusion or empirical experience. If you really want to make reinforcement learning successful, a success, then you need to allow the agent to interact with the environment, allow a large number of interactions. So every row of trajectory, you need to allow the agent to interact for a lot of actions. So you need to make sure the rollout is long enough. Then you have the problem, right? So here is a testing evaluation. So the x-axis is the number of interactions, and y-axis is the number of accuracy. So you can see a very clear trend, right? If you allow the agent to run more interactions, you have high accuracy. So that's the same for training, right? So during training, you also need to allow the agent to sufficiently explore so that you can observe the improvement of the accuracy and the performances. And then, so in a searcher, we allow 128 actions per rollout. And then you have the tricky thing here. So you need to ensure the agent can do a lot of actions in order to get a final good performance. But then you have the question is, we have statistics. is you really observe a long tail behavior of the statistic of the rollout. What does it mean? So in a batch, most of the rollouts take like 10 minutes or 20 minutes. It's okay, but you really have such a long tail rollout. It takes like 1 hour or 2 hours. Why? Because it's a 128 search, and sometimes you query the Google search engine, there's some delay or whatever thing. So it's such a long tail. So imagine what does it mean, right? Imagine if you have a batch of data, right? You have a batch of prompt. You send this batch of prompt to the agents to ask it to simulate the interaction with the environment and get the data back. And every batch, you have one prompt or two prompts take 2 hours, right? That means the whole batch would take 1 hour or 2 hours. You only have 24 hours a day, right? So you only can do 12 updates for the models, and that's ridiculously slow, right? So, so this is majority of, even if the average is like 10 minutes or 20 minutes, but you have such a long tail. So your GPU, you are basically wasting a lot of GPU computation. GPUs is expensive, all right? You don't really want to waste any GPU resources. So it's super, super slow. Well, definitely you can cut the maximum amount of interactions, and then you hurt the final performance. So this is the trade-off. Okay, so think about how you can implement this, right? How can you implement this? So the simplest one to implement this is you can, I have a batch setting, right? I have a batch of prompts and send it to the simulation, get the data back, and then run training, right? And then you have this kind of heterogeneous lengths of different routes, and some routes take 1 hour. So this way, it'll be very slow. Right. Some people will say, okay, I can improve this. I can improve this. For example, when I finish the shortest route, I can immediately start another one, right? So we call this asynchronous rollout. And if you're familiar with reinforcement for LLMs, there's a famous toolbox called Vero. It's from Volcano AI from ByteDance. It's called Vero. It's the most popular training framework. It's basically using this. It's batch reinforcement learning, and within each rollout batch, it can run some asynchronous rollouts. So if after you finish one rollout, you can start another one. It's good. It's good. Definitely, async rollout is better than sync rollout. But the problem is still there. Imagine in a batch, you have one rollout take 2 hours, right? So asynchronous of the rollout within a batch doesn't help anything, right? It doesn't help. So it's still very, very slow because you have a super long, super stale the rollout, right? So it's pretty slow, and you can't do anything with that. So very slow. So so we conclude that. But the challenges, one is no data, right? The second is very slow. So how to solve this, right? So a searcher basically give you the high level idea of how to solve these two challenges. One is there's no data, so you have to synthesize the data. So you need to synthetic data set to create some data, to mine some data, to train the agent. The second thing is because it's super slow, right? You need some new training paradigm or training algorithm. We call this fully asynchronous reinforcement learning, so that you don't need to waste any GPU resources. Okay, so let's go to the details of how we address these challenges. The first thing is synthetic data. We need to synthesize some data set to training. So this is how our project doing, right? We construct a agentic workflow or pipeline, a data creation pipeline. So it's a search question, right? Search is kind of simple because you can basically every question have an answer. So we start from the answer, right? We start from the answer, from a fact, right? That's the answer, and then we construct a question, and then we iteratively make the question more challenging or more uncertain. And then we also have a data quality checking pipeline. So make sure the answer is correct, or make sure the answer is neither too hard or neither too easy for the model. So we iteratively create a data set create this data set. So always we can get a suitable data set for training the current model. Let's take an example, right? For example, here is a question. Say, when was Michael Hearn born, right? It's a super simple question. And this simple question may be very easy, right? So we do some change. We find an entity called Michael Hearn, right? So we replace this entity with a description of the entity, right? We can create that from some other facts. So basically from this one, we replace entity with a description. So we change the question to something, when was the individual born, who, blah, 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 right? So this is a more complicated question, right? Right. Basically, we get this fact from the Michael Horn's Wikipedia page. And then we can do something similar, right? We find another entity called Cat Hill Mountain Railroad, right? We can replace that with something like a historic mountain railway, right? It makes the question uncertain. And eventually continue doing this, and then you will have a much, much more challenging question, which requires a large number of search and reasoning steps. So, and definitely if you're interested in the process, all the process of the scripts and data are released online. Okay, so this is synthetic data. And the second thing is about slow training, right? Slow training, how can we address the long rollout problem of agentic IO? So the idea here is we run asynchronous reinforcement training, right? Let's recall the bottleneck, right? The bottleneck is you have super long rollout. So as long as you put everything within a batch, your batch have to wait. So we want to kill the bottleneck. That is, we don't want any GPU to wait. We don't want to waste any GPU resources. So we call this solution asynchronous reinforcement learning, or the system is called Aerialite. So the key idea is we have two separate resources. We have two sets of different GPUs. One set of GPUs for generation or basically simulating agent to interact with the environments. We call them inference servers. And the other of GPUs will run training, right? So how can we do this? Here is a brief demo. So all the servers, inference servers, are just continuously doing simulation of the agent interaction with the environment. So we have a bunch of rollouts. Some rollouts are short, some rollouts is tough. Once you finish your rollout, we will send this data to the training set engines. There is a data buffer to keep the coming data. And once you have sufficient data, you run a training step. So because you have sufficient data in, so you run a training algorithm, a gradient update step to the model. At the same time, the inference servers will continuously producing new rollouts. There's no stop. And once you update the model parameters, because for example, you change the parameter from the green one to the blue one, right? You have a new set of parameters. And then, you want to sync the latest weights of the new models to the inference servers, right? So you have basically a short pause of the inference servers. You say, okay, guys, you stop because the parameters are updated. So please continue rollout using the latest parameters. Okay, so the pause is pretty short. The transfer of the weights is basically only 3% or 5% of the total cost. This is pretty lightweight. So you do a short pause, sync up all the weights, and then some rollouts is in the middle. It's okay. You just pause it using very short period of time, and then all the rollouts will continue roll out using the latest parameters. And from that checkpoint or that pause, after that, all the models, other inference servers are using the latest models. So continue doing that. And then, in the training engine, you can continue collect all the data. And once you have new data, you just, continue the next training step. Then you have a new model. And again, you sync up all the models to the servers and continue doing this. And in this way, if you can really balance the resources, so from inference and training, and roughly the generation speed and consuming speed are roughly the same, then this whole process, there is no wait. There's no wait at all. The training will roughly continue doing that. And the inference, there's no wait. So you can fully utilize all your GPU resources with no wait, with no resource idle. So we call this fully asynchronous reinforcement learning. It's basically you have a streaming rollout because there's no wait, and an eager batch to training. So every time a batch data is ready, then you run training, right? And then you can basically achieve no wait reinforcement learning. And then you don't need to wait, so it's super fast, right? Super fast. This is from a system perspective, right? So this streaming system is super fast because there's no wait. There's no, you fully utilize all the GPU resources. But every coin has two sides, right? You change basically because you're changing the algorithm, right? if in the batch reinforcement, all the batch setting, right, all your NLP tasks, pre-training tasks, or vision tasks, every data from a single same batch, right? But in this streaming or fully asynchronous reinforcement learning, you have one challenging point here, is one particular rollout, right? One particular rollout can across different model versions. It's very possible that you have very long rollout, and during that rollout, the model has been updated multiple times, right? And previously in a batch IO, it's all the rollouts are created by one model. But now, because you want to make the system fast, right? Essentially, you have a rollout that across multiple versions, right? For example, this rollout across like 3 different versions. And what is this, right? What's the impact of this? The problem is that there's an important concept called the stillness. And the stillness, it's a very classical concept in asynchronous reinforcement learning. Stillness denotes like how many model versions a single data point is covered. And the conclusion is, if the stillness is high, then the performance drops. Super simple. So if you directly run classical reinforcement learning, if you do not do any algorithm changes, you just apply the standard reinforcement algorithms, you can simply observe that as long as your stillness or max the stillness is increasing, then performance significantly drops. That's not what you want, right? You want a faster system can give you a good quality of the training, right? You don't really want a faster system that hurt your performance. So that's something you need to do, is we call this system and algorithm co-design. It's very interesting, a new paradigm of designing reinforcement algorithms. You can design system and design an algorithm all together. So we do so in addition to the system changes, we have a asynchronous system. We'll also do some tiny changes to the algorithm so that the algorithm can handle the stillness. So this is how we change the algorithm with very tiny changes. I'll give you the details. But with the new changes, just like one line of code change, and then you can basically have stillness up to version 8 versions without any hurt of the performance. So, and this is all training performance. You can see that basically if you have stillness of 8, you're still safe without any hurt of the performance. So how we do this, right? So we call this interesting paradigm of system algorithm co-design. From the system side, what we need to do is we have a centralized controller here. That is, we want to control, we have a parameter of the system. So the parameter specify the maximum allowed stillness of the training data. So the controller will pass through all the data. If you have really a super long rollout, right, you have to wait. You have to slow down the whole system to wait the super long rollout to finish. Why? Some people may, okay, can you just throw out the super long rollout during reinforcement training? No, because if you are throwing out data, essentially you're doing rejection sampling. You are injecting a very bad bias of the data, and then all the data will injected to the models. So please don't throw any data. So the system side will need a controller here. If you really have a very long stale data, unfortunately have to wait. But this kind of thing is very rare, right? Okay, so this is system side. You need a controller of the data stillness. The second thing about is the system, the algorithm side, right? So the algorithm side. So let's see what need to change if you really change a own policy algorithm to a fully asynchronized reinforcement training system. Okay, here is if you're familiar with the reinforcement training, here is the objective of a classical reinforcement algorithm. There are 2 terms. The first term is important sampling. It's basically, it's just computing the expected reward. The second term is KL term. Sometimes it's called a trusted region. The incentive of the second term is to make sure the model is not moving too aggressive from the reference model. Okay, so in the own policy reinforcement or batch reinforcement, everything's good. But now, think about your problem. In our off policy or asynchronous reinforcement training, you have some problem, right? Because the problem is that every rollout can cover a lot of different model versions. So what terms is affected, right? The first term is okay because it's just important sampling. So it's basically okay, just to have some variance is good. So the bad thing is the second term is about trust region, right? Think about you have the trust region is the current policy. You don't really want the current policy moving too far from the reference policy, right? In a classical reinforcement, all the reference policy are just same one. It's okay. But in fully asynchronous reinforcement, the reference policy can be a lot of different versions. So if you directly apply classical reinforcement algorithm, the trusted region term is basically clipping the current policy to against the different past versions of the reference policies. So that's bad because you are doing trusted region with respect to different targets. So that makes training super unstable. Okay, so you have to change the second term a tiny bit. How can we change this? Well, okay, that's it. So that's the challenge, right? So we need to do some change to the second term in order to stabilize the asynchronous reinforcement training. How can we do this, right? We just a lot of people have studied this before, right? We are not the first one to study this. So we check some papers. There are some very standard papers. For example, in OpenAI's 2021 paper, basically suggests that okay, so you can using the exponential moving average of all past versions as the reference policy. So to stabilize training. This is a very good paper. It's a very high quality paper in 2021. But think about it, in large language models, this is kind of unacceptable. Why? Because exponential moving average is another large language model. It can be 32 billion parameters, right? So it's very expensive. So in the large language models, you don't really want another copy of the large language models. It's super expensive. So what we do, okay, we do a very, very simple things. Okay, we just use the latest policy as the reference policy, as the reference. It's a little bit more aggressive, but kind of okay. It's kind of okay. So that's what we do. So if you really get that right, you have a system design, you have an algorithm design. If you combine everything together, you will have IR right for the agent models. Basically, we observe like 3 to 5x speed up, like 5x speed up. So imagine you have 24 hours, right? Then you basically, now you just need like 6 hours or 5 hours. It's super, super fast. Okay, so you have very good high qualities and can also observe the emergent behavior, just like some like the agentic tasks, just like the search, the R10, this kind of thing. You can observe some like this kind of emergent actions or reasoning tokens, similarly agent I or agent task. So that's good. That's it. Okay, some final advertisement of our training system. This is open source project called Ariel Light. It's lighting fast, we call it Light. So it's a fully open source. We open source all the data code model, and it's super fast and also very, very flexible to all this kind of different algorithm changes to different kind of agent workflows. So some takeaways of today's talk. Hopefully we still have a lot of time for QAs. Yes. Okay, so some takeaway message. So in this talk, I'm introducing a reinforcement learning training recipe for building up an agent, right? So the data and long horizon rollout is the key difficulty to agent IO. So you have to, so every agent task, you have to think about how to construct data. You need to think about how to handle this kind of long tail rollouts. But IO is good because IO, if you really can solve these two challenges, and reinforcement learning can really give you a lot of good things, give you high performance, give you strong, interesting emergent behaviors for agents. Okay, so here are our projects, and welcome to check it out. And we also welcome to your contribution to our open source projects, and all the questions are welcome. Okay.
Okay, great talk. So any questions from the audience? Yeah.
Thank you, Professor. I have a question for synthetic data part. So how to make sure all the synthetic data came the same difficult level, and also how to guarantee the data quality to for the out of distribution situation.
So the quick answer is no, you cannot control. So I would say something like this. The statistics is I think eventually we created 10 millions of different query pairs. And eventually we only use like 10K, only very few of them. So for the important thing for reinforcement training is that you always need to make sure the training data is right on the boundary of model capacity. So if the answer is too simple, throw it out. If it's too difficult, throw it out. So the evaluation parts is very important. So so my suggestion is always you first need to build up a evaluation process. So I think eventually we finally filter out a lot of data. Only so I think we do I think we filter out all those. So basically, we only keep the data is if you run 32 rollouts of the agent models, and only like 1 or 2 rollouts are correct. So basically, we keep all this data, this kind of data for training, and that give you the best performance. So and definitely you will throw out a lot of data.
But does it look like that if the question is too easy or too difficult, we will throw out, but how to evaluation the difficult level?
Well, simple question. So the simple answer is you just roll out. If the model has some positive probability to roll out the correct answer, but also the probability is very low, that's good. That's good, right? But ultimately, you want something is you really want the model to solve some questions that originally the model don't have any chance to answer it correct. But interesting thing is you really can observe some emergent capabilities. So you need to do some dynamic filtering. So in our training phase, we do a 2-stage. I think there's a plot here. We do a 2-stage training here. Yeah, so we do some 2-stage. So in the first stage, we're throwing a lot of data. There are some noisy data, but in the second stage, we filter out all the noisy stuff. Only leave those hard but not super hard questions, and eventually the model can learn a lot of capabilities. Yeah, so we really can observe some models, some questions from the second phase originally was too hard for the model, but during the first stage of training, the model start to learn something, and that's good. Yeah. So ideally, you need a curriculum, something like that. So dynamically, always you have tons of the questions, and you can always feed in the right one with the right difficulty.
Okay. Yeah.
Fantastic talk. I have 2 questions. The first question is regarding the data set construction pipeline. Do you have the question and answer pairs, the ground truth answer pairs for each question?
Yeah. So the search is some simple task. You can have verifiable answers.
Oh, I was just wondering about the Olympic medal case because it doesn't seem like that would be in the data set.
So that's a test set. That's the test set,
Okay.
right? So yeah, so that's from the test set. Yeah.
And my second question is regarding the training stage. Do you bootstrap your model with supervised traces, or do you just
No, just end to end.
Oh wow.
Yeah, it's end to end. Yeah, but I agree. Sometimes you may need some warm up training to incentivize the model. But you can basically observe this training curve. So in the very beginning, the number of actions is very small. So the model doesn't have any incentive to do like 100 queries. But during training, you can see the emergence of this kind of double check, cross-checking behaviors. Yeah, this is incentivized.
Okay, go ahead.
Wait. Oh, okay. I think I didn't get the why the async the async IL is necessary. Because I think why don't we just collect the whole trajectory in a separate GPU and then just replay when training, so that we can group the trajectory with similar length together in a batch.
Well, so I have to say, so just maybe check this again, is the bottleneck is not about training. It's rollout. And you don't really know which prompt like will take how much time. So the question is really you have a long tail statistics. So some data really takes like 1 hour, 2 hours. And it's pretty unpredictable. This is reinforcement learning because the model is exploring, right? So then how can you do? So you can't really know. So if you know which prompt can give you long output and which prompt can give you short, that's okay. That's okay. But in fact, it's no. And even you know this, imagine you have a statistic like this. It's a super long tail. You have a rollout take 2 hours. It's still right. So you still have the problem. So as long as you have the batch IO setting, right? You want to collect that batch of data. Imagine in your batch, always one rollout take 2 hours. And how can you do this? It's still very slow. Your batch is slow. So the good thing is just break batch. Forget about batch IO. Just do streaming, right? Because you occasionally have 2 hours. It's okay, right? It's okay because you can let it just take longer rollout. And at the same time, you can do training. And that's why you need asynchronous training. Did I answer your question?
Okay, and I understand. Thank you.
Okay.
And push the button on the microphone.
Oh, okay, thank you. So, so I'm curious, have you figured out some potential, the scanning or for during your, just a training process? Because what kind of like a specific model size you think might be sufficient to do the deep research or deep search task here? Yeah.
Okay. So, so in this project with 32 billion parameters.
Okay.
And I can't give you okay, so in this model, in this project with 32 billion parameters, and eventually after training, and you can plug in some tools from Gemini. So at test time, you can allow the model to call Gemini, right? If you can do this, and you can outperform like Kimi 2, outperform ChatGPT deep research, it can be pretty strong. My intuition is reinforcement learning will be most effective if you work with large model.
Much more.
That's my intuition. There's no sufficient evidence.
Because of the language processing, competitive.
Well, I think it's because of the pre-training quality. I have to admit, you still need a sufficiently good pre-trained model, and then the reinforcement learning can give you a huge plus. But if you only have like 1 billion parameters, I think the pre-training is pretty it's insufficient, and then you won't observe too much improve.
I see.
By reinforcement learning. So I think like probably for a good trial, you can try the 8 billion parameter model size, but 32 will be very good.
Okay, 32.
Yeah. Yeah.
Now, currently, like 32 billion models might just good at like for 2 years or MC.
Yeah, I think there will be. Well, I think the Chen 8 billion is kind of okay.
Yeah.
Yeah, but I would say it's smaller than that size. It's just pretty tough, and a lot of the results will be very noisy.
Okay.
Yeah, I would suggest, if possible, and we are doing something. We are trying to see if we can do reinforcement right with low cost, with maybe even larger models. But I don't have a concrete numbers yet. Hopefully, a few months later.
Yeah. Thanks for your
Okay.
Okay. Thank you.
Okay, the last question.
Okay, thanks for the great talk. I have a question, like, because currently, like, people, the community is very passionate about the search agent. So, what do you bet on the next domain, like for agentic RL or?
I would say sandbox. So, well, I have another talk. Well, not in this slide. Okay. So imagine search or all the information seeking agent is essentially doing reasoning within context, right? You have to call a tool, and tool give you some information and put up all the information on your context window and doing reasoning, right? And what the difference between sandbox, right? Suppose your agent have a terminal, right? You can store an intermediate file, right? You can create it can do a local test, right, to run your model. So it's basically expanding the capacity of the model, the LLMs, right? So I would say, so my group is basically shifting from all information seeking stuff to sandbox. I think that's the long run, right?
Okay, sure. Thank
Yeah.
you.
Okay, let's just thank Professor Wu's talk again, so we can then move on to our next session.
Okay.